C-Therm's purpose is to simplify thermal conductivity testing for the materials of tomorrow. Since 2007, we have emerged as the global leader in test instrumentation. Our core strength in thermal conductivity is built on now industry standard Trident instrument and broadened through strategic partnerships with Rigaku and Metrovid, providing one of the most dynamic portfolios in thermal and mechanical analysis.
Thermal conductivity describes a material's ability to transfer heat energy through conduction. In electronics, whether you're developing a smartphone, aircraft, or electric vehicle battery pack, the thermal conductivity of the materials is a major factor in the overall thermal management of the device. In other applications, like metal hydrides that are used as hydrogen storage media in fuel cells, the thermal conductivity impacts the kinetics of hydrogen adsorption.
The most common mistake we see in industry is applying a good method of measurement on the wrong type of sample. This is what happens when you're limited to a single tool and are facing a variety of sample formats. The Trident was designed to provide researchers with multiple options on a single instrument platform, so you always have the right tool for the job. It's been a huge success. Leaders like NASA, Adidas, Intel, Kimberly-Clark, Lucid Motors, and universities around the world choose C-Therm analysis tools and the support we provide.
C-Therm customers get access to the most advanced transient methods and are able to test under real-world application conditions, including humidity, temperature, or pressure. C-Therm's patented MTPS single-sided sensor is the fastest and easiest way to measure thermal conductivity. The Flex TPS is brilliant for more challenging applications and testing anisotropic and thin film samples. Our needle probe offers robustness for polymer melts. And the new THW is great for low viscosity fluids like engine coolants.
Not every client's ready to bring testing in-house, so we also offer industry-leading testing services here at Thermal Analysis Labs. C-Therm's highly skilled and experienced team provides access to the most advanced characterization tools for thermal properties and the expertise to make sense of the test results. For example, Rigaku's breakthrough sample observation capabilities allow users to video record a sample as it undergoes a heating cycle. When working with an unfamiliar material, you can see phase changes, crystallization, and other phenomena. This is vital for understanding the material and helping tell the story of how it behaves.
Metrovib's line of DMA offers the broadest frequency range and the highest force available on the market. This is just one of the reasons it is the standard in the rubber and tire industry. We work with a lot of folk developing different fillers for tires, including carbon black. And due to its sensitivity, the DMA is by far the best method to measure the glass transition point.
C-Therm aims to help accelerate material research and improve outcomes driven by better material performance data. Let us help you get the best possible data for your research. Simplifying thermal conductivity.
Alrighty, hello everyone. Hope everyone can hear me and see me okay. Apologize for any technical difficulties previously. I'm sure you're used to seeing my colleague Ariel on these webinars, but he's not with us today. So my name is Emma Mattinson. I'm an analyst here with C-Therm Technologies, and thank you all so much for joining us today and taking the time out of your day to be with us. So I'll get started here. It's around 2 o'clock on our end, so we'll get started with the formal webinar for today. All right, so today we're going to be talking about differential scanning calorimetry. Just a couple housekeeping items before we start. We will have a formal Q&A session at the end today, so I advise you to make use of the chat box, and we'll get to all the questions at the end. As well, the session will be recorded and available for playback later on, so just keep that in mind as we make our way through the webinar today. So I'm very excited to have a guest speaker with us today, Dr. Genesis Infante. He's the Laboratory Services Manager here at C-Therm Technologies. And he'll be walking us through a very high-level introductory session on differential scanning calorimetry. So theory and applications and all the background you might need. So before we get started, for anyone new on the line today, I'll just give you a quick introduction to who we are here at C-Therm Technologies. So our main concept here is thermal conductivity. So we consider ourselves to be experts in thermal conductivity, and we focus on transient methods of measuring thermal conductivity. So these have their benefits compared to the traditional steady state methods. And worldwide, we have about 2,000 customers and a large network of distributors to help us with all of our customers' needs. So anywhere you are in the world, you'll be well looked after with our distributors. So we aim to simplify thermal conductivity testing for the materials of tomorrow. And this device here, it's called our Trident thermal conductivity instrument. This is our flagship product. So this is what we're really focused on here at C-Therm. It's a modular platform, so it has 4 different possible sensors that it can be equipped with to give the user a really diverse range of applications, and for many diverse sample types and sample environments and representative conditions, our sensors are great for many different applications that you might have. So moving forward here, this is a quick quote by Abraham Maslow that we really like to use and really embodies the Trident system itself and what we do here at C-Therm. So when all you have is a hammer, everything looks like a nail. And our customers often come to us, and sometimes they have a really, really great sensor, a really great method of measuring thermal conductivity, but you're using it on the wrong sample type. So this is why we offer the modular platform with 4 different sensors so that you can really make the best choice depending on your sample and your intentions. So if you're new to thermal conductivity testing, we have a method selection guide. This is available as a free download on our website. And it has all the options for different testing methods, and it's a really great overview of the services we offer here at C-Therm. So I advise you to take a look at that. As well, we work with a couple different partners here. So we really pride ourselves on having a diverse range of material characterization services. So the webinar today will be focused on our DSC from Rigaku, so our partners in Japan. They have a really excellent range of thermal analysis equipment. So DSC, STA, TMA, and we're proud to be the exclusive distributors of these devices within North America. Additionally, we have our colleagues at Thermal Analysis Labs on site with us here at C-Therm. So if you're not quite ready to make a capital purchase on a piece of equipment, or you're not exactly sure how well it would fit into your lab at this stage, we offer a full range of contract testing services, DSC, STA, DMA, thermal conductivity, and effusivity. So anything that you might need, we have many people on hand here to help you with your characterization, and we offer many, many different services. I'll also mention that we are partners with Metrovib out of France. They offer dynamic mechanical analysis, equipment, and testing. Really, really great line here. Some of their equipment is completely automated, so you run some tests, walk away, and it does all the work for you. So really great, really proud to be partners with them out of France. So while you're watching this webinar, if something really jumps out to you as really interesting, or you think you may have a applicable situation there with your sensors or with your samples, I'd be happy to connect you with one of our subject matter experts and schedule a technical consultation. So it's really great. There's lots of resources online, but we really enjoy having one-on-one conversations with our clients and discussing your specific needs for your samples and your intentions. So feel free to reach out to me at any time as well. If you're liking what you see and you're ready to talk about a budgetary quote, we have resources for that as well. So we'll get into those a little bit later. I'll provide you with some links to those landing pages. Finally, I'll just cap this introduction off on client testimonials. So we really like to hear all the things that our clients have to say about us at C-Therm. So this one is from Dr. Enrique Jackson from NASA. He says, we purchased the C-Therm thermal conductivity analyzer after seeing a demonstration of how fast and easy it is to operate. The instrument provides unequivocal results and provides the flexibility to test powders and liquids. In terms of our satisfaction with the purchase, I'd give it a 10 out of 10, extremely satisfied. So that's really great to hear from one of our customers at NASA. And without further ado, I will introduce my colleague, Dr. Genesis Infante, to go over the theory and applications and introduction to differential scanning calorimetry. So I'll hand it off to Genesis now.
All right, so sorry about the delay. Hello everyone. Again, my name is Genesis Infante. I am the TALS Lab Services Manager, and I'll be doing this webinar talking about the basic theory and principles of the differential scanning calorimetry. So my hope at the end of this talk is that everyone will have a better understanding, at least on a basic level, of how the DSC works and how DSC can help you with your thermal analysis needs. And hopefully everyone will be better equipped and will have a better knowledge at the end of the day. So starting with the basic question, what is DSC? So DSC is the differential scanning, stands for differential scanning calorimetry. It effectively quantitatively measures the physical and chemical changes in a sample in response to a temperature change. It could be endothermic, exothermic, or it could be change in the heat capacity itself. So the basic concept of the DSC is that it measures the difference in the heat flow provided by the machine required to increase the temperature of the sample and a reference. So typically the reference would be a blank. So it's just an empty air that would cancels out any systematic error associated with the introductions of the machine itself. So for basic principle, shown right here is one of the example of just the DSCs. In this case, it's from our partner Rigaku, so their DSC Vesta. And what it is that its most basic form. The DSC is an instrument that subjects a small amount of sample to a variation in temperature, and again, to measure how it responds to that change in temperature. Based on that is that typically what happens is that the sample is inserted into a metallic or a ceramic pan or crucibles, and then with an empty one without any sample there inside the DSC test cell where the data is then collected. The thermocouples are shown right here where we can monitor how the temperature changes are across different times. So the DSC itself exports information on the temperature and the heat flow itself through the user interface. And again, I mentioned earlier, to remove the effects of a systematic bias from the machine itself, it is important that we do a reference sample altogether with the sample crucible. So this way, we can compare and subtract the heat flow introduced by the sample on its own. And then this information will tell the operators of how much energy is released or absorbed by the sample and how the sample is changed with temperature. So just some nomenclature for the rest of the webinar would be, I will be referencing a lot on the terms heat flow in this case. In this case, it's a normalized heat flow. So it's basically the amount of heat transfer. In this case, we are normalizing against the unit mass of the sample. Specific heat capacity is effectively the amount of heat required to added into or removed to a substance or sample to change its temperature by 1 degree C per unit mass. So that's why it's expressed in joules per gram per Kelvin. So shown right here is a typical DSC test graph. So what I would like you to focus on are the axes right here. So on the horizontal axis is typically going to be in temperature or sometimes in time scale, but most of the time it's on temperature. And what's shown right here is on the y-axis, on the vertical axis, is the heat flow, again expressed in watt per unit mass, so in this case gram. Another key important information usually that are specified in any DSC graph is this note of the orientation of the graph itself. So it says XO up. So what it means is that any change in a temperature in a positive side, and so basically increase up, would be an exothermic event, and anything on the opposite of that would be endothermic. So it's just a convention. This sometimes it's the opposite, where it's endo up, and so it's just like it's a very important thing to kind of like to note when you're reading a DSC graph, to ensure that you're reading it correctly and in the right direction. So what I'll be showing now is that, as I said, the DSC provides a energy and heat flow into the sample, and what can do is that we measure how the heat flow changes as we're introducing this energy into the sample. So one of the few common changes would be something like a baseline shift. So as you can see right here, the heat flow is introduced, so it's a straight baseline, and then all of a sudden that changes down here. So what it tells me is that like the sample itself underwent some sort of a transition. The heat capacity of the sample somehow changed, and this is a very typical phenomenon in polymer transitioning. So more specifically, through some sort of a glass transition. So some softening phase maybe, or the other way around. So again, one of the more common phenomena that we monitor with the DSC is an exothermic process. So related to that directionality right here, change in the heat flow in a positive sense is that somehow there is a heat release occurring. So this excess energy is captured by the DSC. And it could be anything from, like, for example, a crystallization process. And the opposite is also true, where now the heat flow detected is more in a negative side of things. This is typically associated with endothermic events where the heat is absorbed. So some sort of a phase transitioning change or something like in a melt process is very, very typical on this kind of like shape in the graph. So moving on, now that so as I mentioned, DSC is very useful in monitoring the heat flow by itself. But one of the key features of the DSC is to also characterize the sample's heat capacity. There are several ways that heat capacity can be derived from the DSC, and highly depends on the type of DSC that we're using, the process, and the method itself on the test procedures that we employed. So one of the more common method used is what we call the sapphire method. So effectively what it is, it calculates the sample's unknown heat capacity by a comparative method, what we call the sapphire method. And the reason why we use sapphire in this case is that the sapphire is a very reliable and it has a very stable heat capacity value across a very wide range of temperature range. So it's a really ideal material to use as a reference in this case. And how it works is that typically you do a baseline DSC test. So in this case, what you would do is you would run a DSC test where there's only blank crucibles to characterize what does the system contribute in terms of the heat flow in general. And then you run what we call the standard sapphire test. In this case, you insert the sapphire into the crucible and run that and see how it behaves. So one of the few examples is shown right here. This is referred back from this paper where they're measuring a magnesium oxide content. And they've done a sapphire run and to characterize their material's heat capacity. So they ran a sample shown right here, and in this particular rate. And by subtracting the baseline into the sapphire DSC curve, we can derive the CP of the sample. So it's usually how the equation is expressed this shown right here. Another way to kind of like derive CP is as this what we call the modulated DSC, or also commonly referred to as the dynamic DSC. So this is a modified or an improved version of the classic DSC run, such as the sapphire method. And what it is that you introduce a overlaying sinusoidal or oscillating temperature control over the constant rate of in the heating rate. And what happens is that instead of having a linear heat rate increase, what you get is this kind of like sinusoidal behavior right here. So the biggest advantage of the dynamic DSC in this case is that you can obtain or dissect out certain thermal events in case you have overlapping thermal events for the same sample. So it can occur sometimes that like in a classic DSC run, you'll see multiple peak instead of just like a clean exothermic peak or endothermic. And sometimes it's associated with a multi-step transitional process. And for you to be sure that like, how much the contribution of each of these steps is from process A over process B, the classic DSC is not suitable to get that information out. What the dynamic DSC does is that it can separate the components that are attributed to the heat capacity of the material itself or any kinetic component. So it could be a change in the mass, oxidation, any reaction and whatnot. So some irreversible components on the phase change or the process can be sometimes not seen in a classic DSC run. So this is where the dynamic DSC really shine through. And it can also simultaneously obtain both your CP and a DSC in one run. So yeah. So kind of like an important note when you're dealing with any DSC measurements or experiments is that you need to make sure to observe these critical factors. Is that first is that this doesn't matter what kind of DSC methods you're using or any particular instrumentation. It's very important to observe that like a sample must have a effective and very good surface contact with the crucible itself. It just means that we need to maximize any heat transfer introduced by the instrument itself, that transferring into the crucibles and from the crucible into the sample itself. So we have to make sure that like that factor is not going to be significant in terms of error sources. So that means that if you have particularly difficult samples, for example, we just make sure that you have really good contact. Another second most important, I think, is that we need to be able to choose the exact crucibles to be used with any particular samples. So typically, a crucible could either be a metal, like an aluminum or platinum or gold. And those particular metals are, for the most part, inert for most things, but sometimes a sample that needs to be tested at a elevated temperature can be reactive to those metals. So one must be very aware of any potential risk of that happening. There's also other crucibles available commercially, like something like ceramics, for example, are very common. Also, like graphites that are, again, very chemically inert for the most part. So make sure that there's any physical or chemical reaction between crucibles and samples, especially if you're testing over, in thousands of degrees Celsius. Another thing that you, as the operator, can control is that temperature and scan rates can have a very important influence into the quality of the data. Mainly on the resolution itself. So either you're scanning it too fast, or your temperature ramp or temperature rate change is too fast or too slow. Depending on the situation, it can negatively affect or positively affect the resolution of the data. So that's one thing that an operator must be very well aware of when you're doing a DSC experiment. And very lastly, typically any DSC instrumentation would have the capability of having a controlled environment in the test cell itself. This usually in the form of controlling the atmosphere around your samples. So sometimes you know that your sample does not really do well under air at really high temperature, but you really want to know how it behaves at that temperature. So you might want to, consider removing air or oxygen out of that equation. Or you can do the opposite of, like, you want to understand how the oxidative reaction really affect the behavior of your sample. So you can also introduce air or more concentrated oxygen or any oxidative gas. So that's something that you can control at your end as the operator. So with that, I would like to kind of just move on and for the more specific applications on how DSC can be applied in various fields and whatnot in life sciences and materials research, starting with a polymer. So DSC techniques are very important in polymer science. It's used to measure many things, characterize how the polymer behaves in a very specific ways, and get many very specific information, such as like heat capacity, the glass transition, melting temperatures, and even like how the material is behaving after exposure to any thermal temperature. So to basically try to assess whether it's stable under that temperature by doing like multiple cycles. Even crystallinity of your polymer is also very critical in some cases. Quality control, that's something that has been used a lot. Basically, it's DSC can be qualitative in a lot of things, but it can also be quantitative in a sense that it can identify whether there are any impurities in your sample. So quality control and the purity in this case plays a lot of DSC plays a lot of critical role in that field. A lot of thermophysical react or strain and like reaction kinetics has been characterized by using DSC techniques. Some of them will be modified outside the classic DSC that I've been showing so far, but I'm not going to go over it. But like showcase how DSC can be, a very important technique under a polymeric studies and formulations. So One of the specific examples I like to show here is how the DSC was used using the polymer blends. So in this case, from the work of Sohail Madal and Mondal et al., they had a ABS and a polyamide 6 polymer blend, where the ABS is the amorphous mix and the PA6 is the engineered polymer semi-crystalline. And that can, depending on the amounts of the ratio between the two components, you'll have varying behavior in terms of, for example, in this case, is this the polymer or the melt? So at 100% polyamide 6, you can see that nothing really is occurring between 140 to 260. However, as you increase that amount of ABS until you get this 100% ABS, you can see that the peak for this DSC graph is changing across. And effectively, what it is that it's changing the melting temperature between the two different blends or multiple blends. The second graph right here is the second run, and in the opposite direction, meaning the authors heated the blend into up to some temperature and then stop that heating and actually do the reverse. Now it's in a cooling rate and see how the crystallization occurs in this case. So again, different varying behaviors depending on the formulation. And again, this should showcase to you that how DSC can be a very important tool in terms of understanding how your polymer or materials in general is behaving in an under thermal environment. Next would be something like in a pharmaceutical field, more specifically in engineered proteins. So what you see here is that the DSC is being used to measure the thermal change during the denaturization of this engineered protein, for example, and biopharmaceutical products. So in this particular field, DSC is very well known to be like the gold standard, if you say, in measuring like the melt temperature where the protein is melting into the solution, the water-based solution usually. And what it does is that it tells you really critical information on how stable the proteins is. So basically what it is that so the DSC can reliably measure how unfolding of basically the thermodynamics of how the protein unfolding is occurring. So from a native active conformation right here into a more denatured inactive conformation, and how exactly that happens. So a couple things that are typical in this particular application is that sometimes there are multiple structure between the active into inactive forms of the proteins. And it gives a really important insights to the protein engineers on basically on the design of their proteins and how they can like improve that down the road for their future formulation. And what it is that like as heat is introduced in a solution of this active conformation protein, the CP, the heat capacity, slowly and eventually increases into some peak value right here, and at some point completely go down. So the critical important information here is the peak point where it's basically just the melting temperature, TM. And what it is that it's a point where 50% of the proteins are now denatured. So this is a gold standard index used in the pharmaceutical industry, where it can be used as some sort of an index in measuring how stable a protein is. And again, this is like very important in terms of like designing and then understanding how your proteins behave in general. So again, kind of like continuing with the applications of the pharmaceuticals and the food sciences. One of the most important applications of DSC in that field is understanding the chemical or the crystallization behavior of any active pharmaceutical ingredients. So basically, understanding its thermal behavior and characteristics are effectively going to give you insight on how safe this food products or drugs will be when it times to when a person starts inducing it in a large scale. So crystallization behavior typically are very or directly correlated with its physiochemical behavior. So that could mean dissolution rate on how well this pharmaceutical active ingredients can behave inside a body and how it would react. The crystallization behavior is very important to that. How it could be like thermally stable and more importantly, how it can be processed effectively down the road. So this is an example of a DSC scan for both the crystalline and the amorphous form of indomethacin, basically just an anti-inflammatory drug, showing the glass transition form right here. So this is a close-up look. And the crystallization exotherm and the melting endotherm for both different forms right here. So again, this is a very, this kind of like behavior is going to be critical in terms of formulation and basically safety of pharmaceuticals and food products in general. So finally here is an application example of PCM, so phase change materials using the DSC. So for those that are not aware of what the phase change materials are, basically they are effectively materials that undergoes phase changes as temperature are introduced or removed. So in this case, it can either solidify and release some heat, solidifying into a more ordered form. And as it receives more energy from whether, from any other sources really, it can start melting and starts absorbing that heat into a more disordered form. So this has some applications in terms of like thermal storage or energy storage in general. But then if you look at the DSC curves right here, you can see that there's the experimental behavior based on how the CP of the solid compared to the CP of the liquid should look like, and then effectively how it would look like during the melt itself, right? So it's DSC measurements play a very important role in characterizing these PCMs, mainly because of its potential as a thermal storage device. However, there are still difficulties in terms of studying these particular materials, specifically under DSC, mainly because of how it's typically there are low conductivity and there's thermal inertia as you're heating it, and so you have to go back and as the operator, you kind of have to understand that maybe this is a factor that you need to understand and kind of correct. In a way, so the one thing that you can control is to maybe either slow down the heating rate or use a larger sample. So part of the problem with composite materials in general, like a PCM, with fillers and whatnot, is that DSC are done using smaller sample sizing. And what can happen is that sometimes if you're going to sample a composite like this, it's very hard to kind of confirm that that small sample is a representative of the whole bulk sample. So again, DSC can have a complication with that. But from our point of view, it is really critical to kind of understand how we can adjust accordingly and have a better understanding on the exact story of how the transitions are occurring, and how it matches with any observations shown by the DSC. So far, we've only been talking about how the DSC curves can elucidate some important information based on the graphs provided by the instrument itself. But from our point of view, again, it would also be important if we can somehow add another tool to kind of really have another perspective again, better understanding the exact story of how materials and like such as PCMs behave, right? So this is kind of like me segueing into the specific DSC that we've been using in C-Therm's thermal analysis lab. It's the Rigaku's DSC Vesta that specifically has what we have is like a sample observation capability. So shown right here is basically just the technical specifications of what this DSC Vesta can do. So you can operate from room temperature to 725 C. However, if you're going to do like a sample observation, we can do from about -70 to about 350 degrees C. There are other add-ons that we can do, like the cooling units, a UV light, an auto sampler, and a gas selector. But it can also go do a modulated dynamic DSC mode to measure CP, and has an excellent heating rate. And again, it comes with the standard samples and crucibles. So now what I'm going to show you here is a specific example of like how we can apply sample observation capabilities, and how this can like provide better insights again, and how we can better understand how the material is behaving under different thermal conditions. So you can see here, it's the measurement of azoxyanisole using the sample observation. So you can see here, the heat is increased, the one in red. There is an endothermic event where now the liquid turns into a liquid crystal, and another event where now the liquid crystal turns into more in the liquid phase. At this point, there's a cooling rate, so the heating is done. So it will reverse back into its liquid crystalline phase. And as more cooling is occurring, you can see that about 100 degrees C, there is a very huge event that is associated with recrystallization effectively. So right here, it's just turning back to its initial crystalline phase. You can see here now that it's more in a bulk solid appearance from a powder form. So kind of like, I know that it kind of occurred very fast right there. So this is just a snapshot of what exactly happened in that video. So as you can see, the one in the blue is the DSC curve, and the one on the red is the temperature. And as temperature increases, it's very hard to see here, but effectively the material is still this like needle-like crystals, individual crystals, and as the heat occurs, at some point at about 120 or 115 degrees C onset, the sample changed from a solid crystalline into a liquid crystalline. And after that, at about 135 degrees C, the sample changed from liquid crystalline to pure liquid form. And then at this point, it's in a cooling process, so it's going to reverse back from a liquid form back to the crystalline form. So this event occurred at about 135 degrees C, so it's pretty close to the initial event. So that discrepancy could be, the thermal history just affecting that specific number right there. And the recrystallization from effectively from the liquid crystal form is occurred about at 100 degrees C. It's, you can see, a very sharp, very exothermic event. And then another recrystallization from a liquid crystal into a more solid crystal form occurred at about 75 degrees C. So as you can see here, it's like, we can get a lot of information based on just the DSC curve. We can do a lot of, we can infer a lot from that information, but having another source of data such as this, more visualized, more tangible, it really adds into the value of how we can really enhance our insights on this, on how the materials are behaving in general. Briefly mentioned earlier are there tools that we've used or available that we can use. We have the TMA for thermal expansion, but we also Rigaku also offers this STA. So basically what it is that it's a simultaneous thermal analysis tool where you can monitor the heat flow and also the change in mass So again, both of these have the sample observation capabilities. So one of the examples I'll be very briefly show you guys here is the aspartame tested under the STA. So what you can see here is that press OK. So again, monitor here. TG in the green is the measurement of the mass. So you can see here something occurs at this point, and then you can see the slight change in the mass, and also correlate that with the visuals. You can see that it starts browning, and then bam, it turns into liquid, and then you can have a more and it starts oxidizing and decomposing at a really high temperature. So, you know, we can this the whole like a calorimetry techniques are very insightful in terms of like understanding again how the materials are behaving. Finally, one of the example again, this one is another STA run. This is a biopolymer example, and you can see here, and it's a crucible. It's still white, like that. Yeah. So TG run. You can see here, it's still pretty stable up to about 300 degrees C. And as more temperature occurs, you can start seeing it start melting. As you can see here, the current event, and a major oxidation occurs where now you start reacting with the air and decomposition in general. So you have massive loss in mass in this case as at a higher temperature. So yeah, so kind of like closing up on the whole Rigaku lineup is that one of the features offered by Rigaku is that the software can actually accommodate several instruments at the same time. And what it means is that you can actually overlay different techniques and different measurements on one graph. So in this case, there's TMA, there's a TG, there's a DTA, and a DSC graph. And you can really have a better picture of how all of this is really reflecting back onto the material itself. And you know, if you can just imagine, add on to the sampling observation capabilities on top of that. And lastly, I'd like to kind of show off the DSC Vesta UV / auto sampler capabilities that you can part of like an add-on to this. So again, if you're dealing with like multiple formulation, multiple runs, so like, you know, maybe you can take a look at that. So if you're like dealing with hundreds of formulations, yeah, so the prepared crucibles are being deployed into the correct positions with either samples or the blank in this case. So yeah, so at this point, I think this is the end of my webinar. I hope everyone learned something, and you know, I'd open up the floor for Emma here to close for closing remarks.
Awesome. Well, thank you so much, Genesis. That was a fabulous presentation, and thank you all so much for taking the time today to join us. So, just before we get to the formal Q&A session, I'll just go through a couple outro slides here. So, all of our past webinars and upcoming webinars are available on our website. So www.ctherm.com. You'll be able to find our webinars there. They're free to download. As well, we have a tech library, so many different publications from all over the world with folks featuring the C-Therm thermal conductivity instrument. So it's a really great database of publications if you're ever interested in learning a little bit more about how the equipment's being used. Additionally, I would point you guys towards the LinkedIn here. This is where we post all of our latest and greatest news, all the events we're attending, all the conferences we'll be at, and everything that goes on here at C-Therms, we document pretty well here on our LinkedIn. So I invite you guys to give us a follow there, just to keep up with what's going on here. Additionally, I see a lot of folks from the academic sector online with us today. So this is I put the link at the top here. This is our academic support program that we've made in collaboration with our partners at Rigaku. So basically, it's really great if you're kind of outfitting a lab or constructing a lab at your academic institution. The discount increases as you buy more equipment. So STA, DSC, TMA. It was a really great opportunity for us to collaborate with folks in the academic sector. We also offer a $750 student bursary and free training with one of our subject matter experts. So we really invite folks from the academic sector to reach out to us, and it's really a great collaboration piece, and to learn more about you and for you to learn more about us. And if we want to work with folks, we want to help you with your research. So I invite you to reach out if that's something that might be interesting to you. Finally, we have a couple more webinars coming up. So we're running 2 different series at the same time. So a conductive filler series for our clients working in polymers, in a variety of different applications. It's such a diverse range there. So on September 26th, we're going to be showcasing our DMA for polymer testing. As well, coming up, we have a collaborative webinar with MG Chemicals. So Michael Strong will be online with us to talk about innovations in reworkable thermal interface materials, or TIMs. So that will be on October 1st. To continue this fundamental series, which is really great for different students and professors working with thermal analysis and material characterization, we'll have one on October 17th, which will provide you with a background and introduction to transient thermal conductivity measurement techniques and different applications. And then near the end of October, we'll be doing a fundamentals webinar on our DMA as well. So really, really great opportunities for you to either brush up on your previous knowledge or to be introduced to a new piece of equipment offered by C-Therm. Additionally, we'll have some folks from C-Therm all over the world in the coming weeks. So this first one's occurring right now. That's why my colleague Aria is not with us today. He's in Knoxville, Tennessee at the North American Thermal Analysis Society, the conference there. So we have a booth there, booth number 2. If you're in the area, I invite you to stop by and visit Aria. We'll also be giving a presentation at the 10th Symposium on Polymer Encapsulation in Germany near the end of the month. Then we will be out in Korea, also at the end of the month at the K Battery Show. We will be at booth C617 if you're in the area, as well as the North American Battery Show at the beginning of October. So we'll have a couple people go up to Detroit, Michigan, and our booth is 3753 if you're in the area. So we've got people all over the place, and we're more than happy to chat with you and talk about your testing requirements. So now I'll open the floor back up to Genesis for some questions, and we'll get a Q&A session going on. So please, I welcome you to stay on the line if you're interested. And thank you so much again for joining us today.